ready for a week off.
Yeah, it's getting less Friday.
Oh gosh, it was Friday the 13th. Yeah, those are called the quad cats, those black cats, but I think they live around Burris, so I see them all the time.
There was one just sitting outside the stairs when I walked over.
Yeah, I'm like, oh, thanks.
I was like, that's pretty fun.
Yes. Don't you remember these days when calculus was so simple? Don't you remember these days? All right, guys, let's stand up, stand up, stand up. At least it's not raining. At least it's not raining. Stretch, stretch. Look at somebody and say, wake up. Wake up. Say, I'm serious, wake up. Okay, sit back down, sit back down. We have what due today? What time to do? 11:59, 11:59. We have what next? Friday. Quest 5. There's some chance we'll have a Quest 6 the week after, break. And then our Quest 7 will be on finals week. Our Quest 7. For the first time ever, I started teaching in 1984 when you were -18 or whatever you were then. And I've always given cumulative finals. I've never not given a cumulative final. And so, but I just figure with COVID and I've never given quests. I've always given tests and quizzes. But I've just tried to make this a little bit less stressful for you guys. I know it isn't, but I've tried. It's still Calc 3. Okay, last time we were talking about, and there's a big hint on the board, the words. Last time we were talking about the tangent plane. And this plane is so important because if you're down in the domain, like at a point A1, A2, we just were using 2, 3. But if you're at the point A1 and A2, and if you move in any direction away from A1, A2, and look at the tangent vector along that space curve, the collection of all of those vectors must lie in the tangent plane. Does that seem like that might be an important plane? Does that seem like that might be an important plane? No matter which direction you go in, if you look at the tangent vector along that space curve that's created by walking on a line in that direction, the tangent vector at the point 2, 3, or A1, A2, must lie in this plane. Now when I say plane, you say, I hate you, Dr. Martin. When I say plane, you say n dot x minus a equals 0. N is the normal vector, points perpendicular to the plane. A is the position vector. And that's not mean like, okay, if we're looking for a position vector, clearly the plane is positioned here. So I would go out A1, I'd go over this direction, A2, and I would go up to hit the space sheet, f of a1, f of a2. So my position vector A is just a1, a2, f of a1, 2. Does that make sense? Does that make sense? My normal vector, that was a lot harder. We went through a lot of works just going through two arbitrarily different directions. We took the cross product and we showed, irregardless of those directions, we still pointed, that normal vector still pointed either up or down in the exact same direction. And the simplest normal vector is, and it's pretty nice, the last component is just 1. That's super simple. And then it comes to our derivative. It's just our derivative. It's minus f of x at a1, a2. That's the first component. And then the second component was minus f of partial derivative of f with respect to y of a1, a2. Now, do you have to take partial derivatives on this WebAssign? Do you have to take partial derivatives on this WebAssign? You don't know, then you're in trouble, okay. Our partial derivatives, once you understand what it means for y to be a constant when you're taking the partial derivative with respect to x, or x to be a constant when you take the partial derivative, the moment that sits into your head, partial derivatives aren't that bad. Partial derivatives aren't that bad. And then my position vector is just a1, a2, like a3. No, this is on the space sheet. F of a1, a2. And then the vector x in the plane is just x, y, z. And the flashcard, the very thing we ended with last time, was the flashcard for the tangent plane, And it reminds us so much of the tangent line. It's z minus f of a1, a2 equals the gradient, and I'll just write it out in component form, times x minus a1, the derivative in the x direction, evaluated at a1, a2, times x minus a1, plus the, if you guys, this is active learning, plus the y of a1, a2 times y minus a2, y minus a2. Okay, so give me a space sheet. Dr. Warren, what the hell are you talking about? Okay, when I say space sheet, you say, well, let's try this again. Maybe I'll say it in a different language. Sorry, that's probably not politically correct. When I say space sheet, we use something Eastern European, that's politically correct. Okay, if I say space sheet, you say z equals f of xy. So give me a space sheet.
Z equals 3, 4.
So it's got to be a function of 3, 4. That would be 1 point on the space sheet. So I need a space sheet.
No, sorry, so f of x squared.
X squared. Okay, I like that.
1 over y.
Ooh, 1 over y. Okay, so we got that. We got that. Let's make it a little more fun. How about y cubed? Is that a space sheet? I mean, is there any problems with the domain of that puppy? You don't want to be running along the line. Y equals 0. You don't want to be running down here. You don't want to be running down here in the domain along that line because you're going to cause division by 0. Okay, so now what I want you guys to do is give me a point of interest down here that you want to calculate the tangent plane along the space sheet we're not even plotting. Okay, give me a point down here that you want to calculate the tangent plane at. 3, 4. You're so much better than the other class. I said give them the point, and they said 2, 3. And I'm like, okay, guys, that's already all over your notes. So at least you guys said 3, 4. So go ahead, guys, find the equation in the tangent plane. Find the equation of the tangent plane to the surface at the point 3, 4, whatever f of 3, 4 is. The 6 feet rule kills me. Because I could definitely see a question like this on the quest. Yeah, I did the hardest part. Okay, I want to figure out how high up we hit the space sheet at. Well, I evaluate the function at 3, 4, and I got 3 squared over 4, which is 9/4, and 4 cubed, which is 64, and then we got to get a common denominator, and so 4 times 64, like you can't do that in your head, Dr. Warren. Oh yes, you can. 4 times 60 is 240. 4 times 6 is 24. So 4 times 60 is 240. Okay, and 4 times 4 is 16. So the distributive property, you get a 256. Okay, so I get 265 over 4. That's how high up on that space sheet I am. When I'm out here at 3, 4 and I look straight up, if I could fly like Superman up, 265 over 4 feet, I'd be on my space sheet. I could be up on my space sheet. Now, that would go in this location. Does that make sense? That would go in that location there. So I know at least this part of the tangent plane would be z minus 265 over 4. Now to get the other side, I got to calculate the gradient. Now you guys help me out. What is the partial derivative of f with respect to x? What is the partial derivative of f with respect to x of this space sheet you created? Well, wherever you see a y, you're going to treat it as a constant. So this we'd be thinking of this as like being 15, and this as being a 7. And so I've got the x squared. And so if you take the partial derivative of this with respect to x, what's going to happen with that guy? He's going to go away. That's 0. And here, the 1 over y is a constant. So I'm just going to get 2 x over y. I'm just going to get 2x over y. Because the 1 over y is just a constant. Okay, but that's not what I plug in over here. I've got to evaluate my partial derivative at the point, okay, I'm pointing to it, at the point 3, 4. So then if I plug that in, I get that the derivative in the x direction is, 6 over 4, which is the same thing as 3. 6 over 4, which is the same thing as 3 halves, but I'll put it in as 3/4 for your notes. Times x minus, and then we'll understand if you know what we're doing. X minus, times x minus, times x minus, times x minus 3. Okay, now the partial derivative of f with respect to y is a little bit harder. It's maybe not so hard there. How many people own that one? What's the derivative? What's the derivative of 3y cubed? I'm giving you, it's like Jeopardy. What's the derivative of y cubed? 3y squared. The partial derivative of that would be 3y squared. So we know that last term is 3y squared. But this term here, this first term, if I'm looking at that, x squared is a constant. X squared is a constant. So it's like taking the derivative of 1 over y. You could use quotient rule, but it's probably a little faster to think about this as being x squared times y to what power? -1, and there you get a little power rule. So if I take the derivative, I'm going to get a minus x squared y to the negative 2, which is the same thing as minus x squared over y squared plus 3y squared. Now where I see the x, I'm going to put a, where I see the x, I'm going to put a, and where I see a y, I'm going to put a 4. And so, now remember, you guys picked the point, not me, and you picked the function. So minus, I have a minus 9 over 16 plus 3 times 16, which is 48. And I'm not getting that common denominator. I'm not getting that common denominator. You guys are. I'm going to be lazy and put it up here as times y minus, times y minus, times y minus, y minus 4, times y minus 4. Okay, and then if I had any time whatsoever, I would get on this thing right here. I'd get on the computer, I would plot your space sheet. I would plot your space sheet somewhere around the point 3,4. I'd avoid what line? The line I would avoid the most is y equals 0. So I wouldn't be picking a box that would include that. I would plot your space sheet, and then I'd plot the plane z equals where I took this to the other side. And what you guys would see is you would actually get to see, I'd have to go pretty high up. I'd probably have to get pretty high up to capture that. But what you would see is this plane sitting tangent to that space sheet. I mean, it's pretty cool that we can even do this. And this plane is called the what again? The tangent plane. It contains all the tangent vectors moving away from the point 3,4. Is this an important plane if this function was an application? You know, and so is it that hard to calculate though, guys? Is it really that hard to calculate? People are like, Calc 3 is so hard. Calc 3 is so much harder than Calc 2. And I'm like, I don't think so. I don't think so. Sequences and series are like the death of most students. Man, by the time you hit Taylor series, nobody really freaking cares. You're like, I just want this to end. I'm going to go to class and not really focus at all. Taylor series, power series, even though that's the coolest part of the whole class. You know, but as far as like this stuff, yes. It's like, well, the partial derivative, complicated. No, not complicated. You're just treating y as a partial derivative. Wherever I was here. Partial derivative. Did I not put my y? No. I guess I did. What? You guys didn't stop. There should be a y there. Partial derivative. It is complicated when you don't write down document. Partial derivative is really complicated. Not really, you're just treating x as a constant. Yeah, there's a lot of flashcards to remember, and it's a lot of writing, but nothing about it is really that complicated. Nothing about it is really that complicated. Okay, stand up. How many people are following? How many people are following? Okay, and now you're not going to be following. So stand up, look at somebody and say, wake up, wake up. Say, I'm serious, wake up.
Serious, wake up.
Okay, sit back down. How many people think they might want to have that equation memorized? How many think they may want to have that equation memorized by? How many people are going to go home for Thanksgiving? How many people are heading home for Thanksgiving? Let me get up on my pulpit here. Okay, all right, just. Yeah, Cameron, there we go. See, I'm getting ready. I've done training for your device over there. Okay, guys. What can you get for free next Wednesday at U Park? COVID test, not COVID. Okay, COVID test. You can get it for free. You have a Quest win. Friday, there's a 2-day turnaround. Okay, so you can leave next Friday having taken your COVID test and taken your Quest. Okay, and then not take COVID home to the family for Thanksgiving. The turkey and COVID. Okay, have a side of COVID with your turkey, Grandma. Okay, so this is not what we want to do, right? This is not what we want to do. So we really want to go get our free. They have 1,000 of them. There's only like 10 of you here. Okay, 20. Okay, so I'm just saying, I would die. Okay, now we're starting something new. So I need a little commercial in between. So the infomercial was free COVID test at University Park. What time, Dr. Warren? Well, that would be all day. Well, most of the day. Do I have to register? No, but you can. Would I get my test back before I go home? Probably. But you will get your Quest back. I'm telling you, you're going to get your Quest 4 back. No, Dr. Warren, I'd rather get COVID than get my Quest 4 back over break. Okay, I'd rather get COVID. Okay. Okay, a new concept. Draw yourself an XYZ. Draw yourself a space sheet. Z equals f of xy. I don't care what it really looks like. It just can't flip back over itself. So you get 2 z values for one value in the domain. And I guess for just consistency, give yourself a 2, 3 down in the domain. Mark yourself a 2, 3. How many people are caught up? How many people are caught up with me? Okay, now to the best of your ability, it's your imagination, it's your art. Imagine that you go straight up from 2, 3, and you go up and you hit your space sheet. So you're looking straight underneath 2, 3, and you're going to hit your space sheet up there. Then mark the coordinates of that point. Mark the 3 coordinates that would represent that point that could explain to somebody how to get there. Okay, now it's going to get a little more complicated. You're down in the domain. You're at the point 2, 3, and draw a unit vector u, just pointing away from 2, 3. Draw a unit vector down there in the domain with its butt at 2, 3, pointing away from 2, 3. And since it's a unit vector, remind yourself to the side of your notes that the norm of u is 1, because it's a unit vector. Now I think I've lost probably half of you. To lose the other half, draw a line down in the domain, in the xy plane, that runs through the point 2, 3 along that unit vector u. Draw a line, lightly draw a line. Now hopefully your space sheet is not a plane. Hopefully your space sheet has some bendiness to it. But imagine that you're going to plot all the points on that line you just drew, down in the domain, and that would create what up on your space sheet? A space curve. So draw a space curve that you think follows the line. It's really up to you how it looks, okay? But make it go up and down, make it a little wavy, and it's got to go through the point 2, 3, f of 2, 3. It's got to go through that point you plotted up there. And then while you do that, I'm going to catch up. And I want to point out a subtle teaching tip here, guys. I'm going to point out a subtle teaching tip. By me having you do it first, your mind has to be engaged. It's more, you're on the offense. If I'm just drawing and you're just copying, it's more passive. You're more on the defense and you can drift off a lot faster. So keeping your students active, keeping it a little bit blind, actually helps them stay engaged and learn. And you all are going to be teachers. You all are going to be teachers because you all are going to be parents. You all are going to be parents. Right? Dr. When I'm not going to be a parent. I never want to have a child. You're going to have children. Okay, the odds say that you're going to have children. Nick, you're going to be a dad. Just letting you know. Which means you're going to have to do what with your son? Teach, yes. Okay, it better not be, this is the way you open a can, son. Okay, that's not what I want you teaching your son. This is the way you open a bottle, son. No, this is not. Okay. This is what you should be teaching your son. This is a space sheet, son. This is the tangent plane. Okay, all right. Little, oh crap, my brain. Sheldon. There we go, Sheldon. Okay. You're geeks, you know what Sheldon is. Okay. All right, so we're here. Okay, now I ask you to draw a unit vector. So I'm gonna have my unit vector go that way. Over here, I'm reminding myself, I normally do with 1. Then I ask you to draw a line. So imagine I'm moving in that direction. Okay, and then I said draw a space curve that I'm imagining follows that line. So maybe it's coming down, something like that. And I kind of imagine I'm going in that direction right there. And that's where we're at, right? Am I caught up with you? Okay, so now we're going to talk about a new concept. Write down the directional derivative of f, the directional derivative, these are all words, the directional derivative of f in the u direction, and you can use the vector u, in the u direction at, and use the point 2, 3, use the point notation, the parentheses, 2, 3. So we're talking about the directional derivative. Okay, how many people have that? How many people have that, what they have? Now, how many people don't want to write that down every single time we talk about the directional derivative? How many people don't want to write down those words all the time when we say directional derivative? Okay, so we're going to end up with some notation that will mean exactly this. First, it's the derivative. So let's use how about a d for derivative? Are we all, let's not use little d, we've used that up. Okay, it depends on f. So let's have an f. It's in the u direction, so we're actually going to put a little subscript u there. So we got the directional derivative of f in the u direction. The only thing we need now is the 0.23, so we'll just use that there. Okay, so we're standing at the 0.23. We're standing at the 0.23. We're looking up at our space sheet, and right above my head is the 0.23, f of 23, and then I'm picking a direction u, and I'm asking, how is that surface changing? If I make a step away from 2,3 in that u direction, how is that surface changing? What's the rate of change of z? How is z changing if I go in the u direction? Now, if this derivative is positive, what does that tell you about the surface? What's happening if that derivative is positive? Z is increasing. That if you're moving in the u direction, we're expecting our surface to increase in the z direction. If it's negative, then we're expecting it to decrease. So if it's cost, how many recognize, like if you're building something in business, cost may depend on more than one thing? I mean, do you think could cost depend on more than one thing? Okay, so we're saying that if this is the cost, and we're picking a direction, we're at this many units of something. Okay? This many units of one thing and this many units of the other thing. If I move in the u direction, if I move in this direction with units, would the cost increase or decrease? May this be something that an employer may want to know? You're like, I hope that derivative is, you chose the direction u. You're really hoping that derivative, if it's cost, you're really hoping that derivative is negative because you want your cost to go down. If it's profit, suppose it's profit, and you're like, well, I really think we should take our units this way. And suppose it ends up being negative 1,000, okay? Are you a little disappointed? Yeah, if it's profit, you're like, okay, I'm emptying my drawers right now. I'm putting my drawers into a box because I know people are going to be coming and taking me out. I probably should have done a little calculus ahead of time. Now you're like, Dr. Warren, how can I calculate? How many people recognize this is an important concept? How many people? Okay, ask me, how can I calculate this? You don't want to know. Okay, calculus is about, let's just stop there. Okay. It's defined in terms of a limit. So this is the definition. 3 lines needs definition. This is the symbol. You're like, Dr. Warren, what does that symbol mean? Have I taught you nothing today? Did you not say, we're going to use this symbol to represent these, Directional derivative. Read the words. That's what this means. Now, how do I calculate it? Well, it's in terms of a limit. Now you're going to be pretty happy because it's not going to be a vector value limit. It's our old scalar friend. And it's going to go to 0. It's the limit as t approaches 0. It's a derivative, guys. Guess what you're going to have next? It's a derivative. Guess what you're going to have next? A fraction. Okay. And chances are the denominator is going to go to, in derivatives, the denominator is going to go to 0. It so happened that t is going to 0, and so it's just going to be t. Now up in the numerator, we're expecting something like an f of x minus f of a. And the f of a is pretty... You're going to have a minus f of 2, 3. Now, over here, this is a little bit more disappointing. It's going to be the point 2 plus t u1. It's going to be 2 plus t u1. And then could you guess what the second component could be? If the first component is t plus 2 plus tu1, could you guess what the second coordinate would be? 3 plus tu2. And this limit represents what again, guys? This limit is the way we calculate the directional derivative. That seems so important. And you're like, Dr. Warren, please, for the love of God, please, please do not make me use this limit to calculate this thing. There's got to be a better way. Say that. Yeah, there is. But it's not easy to get to. There is an easier way, but it's not easy to get to. Just give us the damn formula, Dr. Warren. Please don't make me understand it. I don't care about understanding. Please don't. I don't care why. I don't care why. I don't know how my car works. I'm happy. I don't need to get in under the hood and know how it works. I turn the key. I push on the gas pedal. Well, I'm not just giving you this. This is called math, and math is proof. Nothing comes without justification. Okay, I'm looking at this, and you're like, Dr. Warren, does this drawing have anything to do with this? Or are you freaking kidding me? Okay. So guys, imagine that I'm looking at this line. When I say line, you say, I hate you, Dr. Warren. When I say line, you say a plus td. Okay, so it's a two-dimensional line. It's down here in the xy plane. I need a position vector that would position it in the plane. You know, like, well, Dr. Warren, how about that guy? Does that work for you guys as far as being a position vector? And what is that vector? And you better know. 2, 3. So we're looking at that. That would be a perfect A plus TD. Well, if I only had a vector that was pointing in the direction the line was going. Oh, wait, we do. It's U. Okay, so this would be T times the vector U1, U2. How many people are following? How many people are following? Okay, now what I want you to do is let's break this down into a vector value function. Let's break this down into, let's do a little scalar multiplication, a little bit of a scalar multiplication, and a little bit of vector additioning, and write this as a two-dimensional vector value function. My wife was like, do not get near the students. And I just can't help myself but look around what you guys are writing. Oh, it just kills me not to be out amongst you and see what you're... See, I learned. It took me 10 years. I started teaching in 1984. Was that more than 10 years ago? I'm just asking. Was that, I mean, you're 18? No, you're 20. How many people are 20? How many people are 19? Okay, so 10 years ago, you were how old? 9. Okay, so you were born in 2000, 2001? 2001, okay. I started teaching in 1984, okay. 10 years ago, when you were 9, okay, I figured this out. There's a choir effect in the classroom that I didn't realize until one day I was teaching, and I said, let's do some active learning. So I asked kids to do stuff, and I started walking around the room, but I just kept quiet. I just kind of wandered around, saw what people were writing, wandered all around the room because it took a little while. And then I noticed, like, 2 people had the right thing. 2, okay? And we're talking like a full class, because like 35. Typically I have 35 kids crammed in here because I have one of the worst attendance policies on the planet. Except COVID. You know, no, come when you want. It doesn't matter, come when you want. And then I'm like, okay, I asked for the answer, and I'm writing down, and then somebody starts talking, and 35 people are giving me the right answer, and I'm like, wait a second. I just walked around the room, and there were 2 people that had the right answer. 33 of them knew nothing. And then I'm up here going, and I'm like, and then they kept talking, and everybody knew it. And I'm like, oh my gosh, it's just like when I was in middle school choir. Everybody's mouthing it, but then they're following along because one kid actually knows what they're singing. Everybody else is just there. And so let's go ahead. What is the first component in our vector value function? See, everybody knows. 2 plus t. I'm like, everybody's got this. And then, Okay, now I gotta ask, do you see these anywhere in that? Do you see these anywhere in that? So we've gotta ask, does it seem like this line might be important to our directional derivative? Now I've gotta ask, is it a legitimate domain curve at 2, 3? Is it a curve? Is the line a curve that runs down in the domain? Does it go through the point 2, 3? So there has to be a C where it actually hits the point 2, 3. What's the C value? If this is your R of t, what's the C value that actually hits that point 2, 3? 0. So it's a domain curve because R of 0 actually hits the point that I want. Now we're assuming that the function f, what did I just say? I know the moment I started going that way, everybody's up. When I said, we're assuming that the function f, what did I just say? Is differentiable at 2, 3. We're assuming that the function f is differentiable at 2, 3. Now I'm going to help you for your quest next Friday. Okay, how many people think definitions may be on there? Have we had a few definitions so far? Just a lot of them are in flashcards. But if I ask for the definition, f, the function f, write this down. The function f is differentiable. You can just write diff. We all know what that means. The function f is diff at 2, 3, if and only if, IFF, super fast, there exists that fun backwards E, a D, an element of V, which means it's a vector, not necessarily a direction vector, but I like where you're going. It's a vector. So what do you have written down so far? D an element of V such that S dot T dot. I like your little shorthand, Dr. Warren. Okay, you guys fill in the rest. No, Dr. Warren, you keep telling me. No, active learning. You guys fill in the rest because you may have to fill this in on a fill in the blank. Yes.
So this is the definition, right?
This is the definition. Very good, Cameron. This is the definition of what it means to be differentiable at a point. Now I can't help. I'm taking risks. Since it's a definition, it's probably defined in terms of a limit. Okay, so in my first class, I had like 20 people show up out of my 35. Not a single one of the 20 had it right, even though like one of them had the highest grade on not for this quest. I haven't even looked at that quest, but on the third quest. But nobody had it. So let's try this class. The limit as, you like Dr. Warren? I'm done. Dr. Warren, I bet there's a fraction. Dr. Warren. How many people got that far? Okay, now the limit as, no, we're gonna go there, but that's not the definition. XY, we would write it as a vector X. Approaches, everyone's like, I got that, Dr. Warren. Approaches 2, 3. and I'll help you out. There's an absolute value in the numerator and a norm in the denominator. And does anybody remember what the limit went to? Does anybody remember what the limit went to?
0.
0. What's in the denominator? What's in the denominator? XY. Now we get a good choir going. XY. Now don't keep choiring. It's good. If you say it, it helps you remember. XY minus 2, 3. Okay, now in the top, it's our f of x minus f of a. It's our f of x minus f of a. So it would be f of xy. And now, even though we write it as vectors, we're thinking of it more as just evaluating it at a point. Minus f of 2, 3. And now you've forgotten. And it's the quest. And you're like, oh look, we haven't used the damn. Remember, we got it here. We haven't used the damn d. So minus, it's a vector, so d dot xy minus 2, 3. And let's say you forget. Well, the numerator's got to go to 0 because the denominator's going to 0. The numerator's got to go to 0 because the denominator's going to 0. As xy goes to 2, 3, will these two cancel out? As xy goes to 2, 3, will these cancel out? As xy goes to 2, 3, will the bottom go to 0? And we're here, we're going to have this guy go to 0. How many people remember writing this down? How many people writing? Do you think this is going to be on your quest? Do you think this is going to be on your quest? This is the definition of derivative in higher dimensions. Now, true or false, what we just wrote here is a legitimate domain curve. Dr. Warner, I'm not focused at all. True or false, this is a legitimate domain curve.
True.
Okay, once again, we're going to exploit like we've exploited so many times. If the limit goes to 0, then the limit along if the limit itself goes to 0, the general two-dimensional limit goes to 0, then the limit along every domain curve must also go to 0. The limit along every domain curve must also go to 0. So this would imply, let's use our domain curve. Where I see the x, I'm going to put the vector valued function 2 plus t u1, where I see the y, that component of the vector valued function, I put 3 plus t u2. And we're taking the limit along this thing as t approaches c. So it'd be the limit as t approaches 0. Okay, now you guys are going to fill in. What do you put in for x? What do you put in for y in all of the locations that you see x and y? What do you put in for x and what do you put in for y in all those locations you see x and y? Okay, for sake of time, I would have the vector 2 plus t u1, 3 plus t u2, minus the vector 2, 3. Okay, and then I would have f of
2 plus
tu1 minus
f2, 3.
minus d dot
2 plus u1. That's 3 plus u2.
minus,
2, 3.
and this limit's got to go to, as t goes to 0, as t goes to c, this limit's got to go to 0. How many people are following? How many people are following so far? Okay, so now, how many people can do vector subtraction? Just wondering, how many people can do vector subtraction? How do you subtract two vectors? The components, okay. So what I want you to do now is write down that same thing again. Write down that same thing again where you actually do the vector subtraction. Do the vector subtractions both in the numerator and in the denominator where you have that vector subtraction. Okay, how many people are done? How many people are done? How many people are close to being done? Okay, what do you guys have? Is there really anything we need to simplify with those two terms? Is there anything that there's not really anything I can do with the f's. So it'd be f of
2 plus
minus 3 minus d dot the vector okay, and on the bottom I've got the norm of the vector,
u1.
and then
u2.
how many people got that? How many people got that? And then the limit's got to go to 0 because we're running along the domain curve. Okay, if I look at this, guys, I got a t times u1, I've got a t times u1 and a t times u2. Could I pull that t out as a scalar? Could I pull that t out as a scalar multiplication? Okay, so now I'm going to erase and you're going to hate me. Okay, I'm going to erase and you're going to erase. Let's pull the t all the way out to in front of the d. D is just a constant, so I'm going to get rid of this, and I'm going to get rid of that, and I'm going to put the t there. And you guys can do the same thing. We're just using scalar multiplication. Now, how do you get the norm of the vector 7, 5? How would you get the norm of the vector 7, 5? Square root of 7 squared plus 5 squared. So how could we get the norm of tu1 and then tu2? So now I want you to write down what you had here, but change the norm out for what it is. Change the norm out for what it is. So rewrite everything, scribe it all over. and I got lazy guys in the numerator, I got lazy in the numerator. U1 and U2 I can just rewrite as the vector. U1 and U2 I can just write as the vector U. So you can get lazy too. You can get lazy too. So what do you have down there in that bottom? What do you guys have down in the bottom? T squared, I'll just even do it. T squared U1 squared plus T squared U2 squared. And that limit's gotta be 0. How many people are following? How many people are still with me? Okay, now look at the bottom. Look at the bottom. Let's do a little 8th grade algebra. What's alike in both of these? What's alike in both of those? Look at there. What's alike in both of those? What could I do with that t squared? Take it out. Now, is the square root of apple times banana, if these are numbers, positive numbers, equal to the square root of apple times the square root of banana? Is the square root of apple times banana equal to the square root of apple times the square root of banana? So I'm not going to do this, but if I was going to do this, this could be the same thing as the square root, this could be the same thing as the square root of t squared times the square root of u1 squared plus u2 squared. Don't write this in your notes. Don't write it in your notes. Okay, but u1 squared plus u2 squared is the norm of, Dr. One, am I focused? The square root of u1 squared plus u2 squared is the norm of u, but u is a unit vector, so that would be 1. What's another way to write the square root of apple squared? The absolute value of apple. So that's what I want you to write down. I want you to use the fact, so even though you didn't write this down, you're not going to pollute your notes with that. Right here, I want you just to write down to the side that the norm of u is 1. That'll be enough. That'll be enough. And that the square root of apple squared is the same thing as the absolute value of apple. As long as you have those in the side of your notes, you'll remember what you did at this next line. So I want you to use the fact that you can get rid of the u's down here, and you can replace this square root with just the absolute value of t. And I'll do the same thing. Needing all MIT-ish here. Words are going up and down. Just like you're getting a high quality lecture. Okay, how many people are following? How many people are following? Okay, now, another one. The absolute value of, what's your favorite side dish, Stuart, at Thanksgiving?
Mashed potatoes.
Mashed potatoes. We get a side dish of mashed potatoes here. Okay. Caitlin? Green bean casserole. Okay, so another dish here of green bean casserole. There, yeah, kind of looks like a pie. Okay, so if you have the absolute value of mashed potatoes over green beans, is that the same thing? The absolute value of mashed potatoes over the absolute value of green beans, is that the same thing as the absolute value of mashed potatoes over the absolute yeast? Okay, and then over the absolute value of green beans. So could I take this absolute value? Could I take this absolute value and make it one absolute value? Okay, now I'm going to save myself some steps. Could I, once this t's inside, once that t is in that denominator, could I break this into two distinct fractions? One where I'd have like my f of x minus f of a, and my other one where I'd have a minus t times d dot u over t. And if I did that, what's really nice with this one? The t's cancel. How many people are following? On the other side, the t doesn't cancel. On the other side, the t doesn't cancel. But on this side, the t would cancel. Okay, this is an important result that shows up a lot when you're dealing with limits. If you have the limit of a function, if you have the limit of the absolute value of a function, of really anything, and it's equal to 0, what else follows? If the limit of the absolute value, it's very, very important, it's 0. If the limit of a function is 0, if the limit of the absolute value of a function is 0, then the limit of the, if the limit of the absolute value of a function is 0, this is an if and only if the limit of the function itself is 0. It's vital. You'll never get it to follow if it's like 7. So let's go over what we've done again in our brain. Dr. Warren, I can't follow. Yes, you can play chess. You're in Calc 3. You're an engineer. Okay. How many people are doing online engineering? How horrible is that? That's got to be horrible. I can't imagine online engineering. I mean, like, I didn't sign up for online. I went to JMU, not to get online. Okay. I brought this in as one fraction inside the absolute value. How many people are following with that? I broke it into 2 fractions. What happens with the t here? Cancels out. The limit of this absolute value is 0. So the limit of this function must be 0. So this would imply then that the limit as t approaches 0 of this fraction. Now what's in the bottom here, guys? What's in the bottom? We kind of removed the absolute value right here, Robert, by just going from what was inside the absolute value means just that 0. So down here I would just have a t, and then here I would have a minus d dot u, because the t goes away, is equal to, and this all this limit's got to be equal to 0. Now what's in the numerator? What would be in the numerator? 2 plus tu1.
3 plus tu2.
How many people are following? How many people are following? Now this is just a constant. This is just a constant. A limit of a constant is a limit of a constant is a the limit of a constant is a constant. This is just really the limits here now. But the limit of a constant is just a constant. This is d dot u. Could I take the d dot u to the other side? I don't like the negative. Could I take the d dot u to the other side? And then we finally end up with this result, that this limit as t approaches 0, is equal to d dot u. Do you see that limit anywhere else in the room? Do you see that limit in there? Like, Dr. Warren, that is your, Dr. Warren, wait a second. That is your, Dr. Warren, that is your derivative. This is your, Dr. Warren, how do you say this again? Can you not read? Read. Directional derivative of f in the, at the point 2, 3 is defined in terms of this limit. But I kind of like cheated, pulled the wool over your eyes, and said, oh, you can actually calculate this by doing d dot u. Dr. Warren, if I could only remember what d was. Well, Dr. Warren, it's a vector. Does anybody remember what we found D1 to be and D2 to be if the function is given to be differentiable at the point 2, 3? Does anybody remember what D1 and D2 were? What, can anyone? Choir. Partial derivative of f of x evaluated at, it's a vector. And what was another term we used for that vector? We called it the derivative, and like, we probably technically shouldn't call it. We gave it a new term. We called it the gradient. And what symbol did we use to represent it? Triangle vector, like whatever the hell that means. F at 2, 3. And so we end up with this beautiful result that the directional derivative is merely just the gradient of f at 2, 3, dotted with the unit vector in the direction you're going. Now guys, it is vital that it is a unit vector. Say that to somebody. Because if it's not a unit vector, you're going to have something that's way too big or way too small. Notice, right here, did we not use the fact that the norm of u was 1? To go from this line of logic to this line of logic, did we not use that the norm of u was 1? You know, and so if you're not using the fact that the norm of u is 1, you've got to divide by the norm of that vector at this point. Okay, but that's not the way they write the definition. So it's vital that the norm of u is 1. Okay, so let's try this out. Let's try to calculate our first directional derivative. Why don't you stand up and wake up first? Stand up. Stand up. Stretch. Oh my gosh, look at the clock. Where does time fly? Okay, sit back down. It always flies for the teacher, but never for the students. For the students, it's always like, oh my gosh, that seemed to be like eternity. How many people have sat through lectures where they were just like, I honestly thought I might light myself on fire just to get out of the lecture? Has anybody been there before? Where they're in a lecture and they're just like, or how many people are like in meetings where somebody always has to interject their opinion in every single meeting? And it's usually something completely stupid, you know? But in academics, you just can't say it's stupid. You gotta ponder, think about it, and then couch it in the kindest way simple. That is the dumbest idea I've heard in about 3 years. No, let's not do that. There were a number this semester, in fact. Okay? I look at a number of the decisions. Like, okay, let's just start school. Even though we saw North Carolina implode, let's just start on recording. Let's just start school and believe somehow we've got it figured out. And then 1,000 COVID cases later, we're now shutting down the campus. One weekend. Sorry, that was the dumbest idea. I don't know. So yeah. Okay. I forgot completely what we were doing. We're going to calculate our first directional derivative. So I need a space sheet. So give me a space sheet. Remember, you're picking it, so you're going to be dealing with it. Give me a space sheet. What is a space sheet again? A function of x and y, so you're going to be taking the gradient.
X squared plus y.
Okay, x squared plus y. We better make it a little more interesting than that. We probably should put an x there, just to keep it a little more interesting. Could we plot this? Okay, what else do we need if we want to take a directional derivative? a point. So what do you guys want your A and your B to be? What point do you want to have? 1 and 4. So we're going to take the directional derivative at the point 1, 4 down in here in the domain. Okay, so there's the point down in the domain we're interested in. What else do I need if I'm taking a directional derivative? A unit vector or a u. So let's just not even start with a unit vector. Just give me a direction to go in. It can be any vector, and then we'll make it into a unit vector. Give me a direction to go in. What direction do you guys want to head away from? What direction do you want to head away from the point 1, 4 in and examine the surface on?
1, 0.
1, 0. Let's make it a little more fun, right? I'm afraid the students won't get it for that, but I like where you're going. That would be fun to, nice little unit vector to start with. Give me something, any vector, we'll turn it into a unit vector.
6,
6,
9.
9, okay, so legit vector, is that a legit vector? Is that a legit vector to go in? Okay, so now 6, 9, so if I'm plotting this, I would, from here I would go, if I was plotting this vector, I'd go 6 in the x direction, 9 in the y direction, and then I'd have that vector, but that vector's not a unit vector. But could you make it a unit vector? Could you make it a unit vector? If I'm thinking about the unit vector that points in the same direction, but as a unit vector, I would need to divide 6 and 9 by what scalar? I would need to divide 6 and 9 by what scalar? The norm of this vector, and how would you get the norm of the vector? Dr. Wong, you took away our calculator. It'd be the square root of 36 plus 81, which is 36 plus 81. 117. So this would be 6 divided by the square root of 117, and this would be 9 divided by the square root of 117. Now imagine that I want to calculate how z is changing. What were the words that just came out of my mouth? I want to imagine how the space sheet is changing in the u direction. So my notation would be d u, but my u is that. F of, and what did you guys pick your point to be? What did you guys pick your point to be? 1, 4. So you're trying to calculate, if you move away from the point 1, 4, in this direction u here, in this direction u, how's it changing? Well, where's the thing that'll help you? Where's the thing on the board? Where's the thing on the board that will actually help you calculate this? Where's the thing on the board? Look around. If you had to put anything in there, where would be the thing that would help you? Okay, we got 4 boards. Well, let's try this. Which of the 4 boards would it be in? Which of the 4 boards? Josh is pointing here. There's lots of stuff. There's lots of stuff on here. Is it in the lower half or the upper half? Is it in this side or that side of that upper half? And I think if we did it, it would be that right there. How many people are pretty comfortable with the u now? How many people are pretty comfortable with the u? And how many people think they could take a dot product? I'm just wondering. How many people are like, Dr. I could probably take the dot product. Now, how many people think they might have a chance of getting the gradient even? You got to take the partial derivative of f with respect to, and then you got to take the partial derivative of f with respect to y. So let's just do that really quickly, and we may. What's the partial derivative of f with respect to x? Just look up there. You should be getting better at this. What is the partial derivative with respect to x? What would it be? 2x plus y cubed. Did anybody get that? Did anybody get that? Now how about the partial derivative? How about the partial derivative of f with respect to y? 3y squared x. Now, what numbers would I plug into those partial derivatives? What numbers would I plug into those partial derivatives?
1 and 4.
1 and 4. So wherever I would see an x, I'd put a 1. Wherever I see a y, I'd put a 4. So I'm going to do this quickly. 2 times 1, 2 times 1, 2 times 1.
2.
2. 4 cubed. So I know I have 66 there. Fy at 1, 4 would be 3 times 16 times 1, which is 48. So my gradient vector is 66, 48, and I'm going to dot that with who? I'm going to dot that with who? I'm going to dot that with who? You, with you. So I dot this with, if I dot this with the unit vector, who's the unit vector? Who's the unit vector? 6 over the square root of 17 and 9 over the square root of 17. So if I do this and dot it with this, do you see I have to take great care when I write my quest? So it's reasonable things to calculate doing this. But guys, is it really that hard? Is it really that hard? Is it really that hard? The hard part is understanding why it is what it is. The hard part is understanding why it is what it is. The technical aspect is not much. Okay, so what does that mean? So if you head away from the point 1, 4 on your surface, how is it changing in the 6 over square root of 17, 9 over the square root of 17? And it, well, whatever that dot product is, would it be positive or negative? Would it be positive or negative? So you expect you're probably going to be, as you walk, you're probably going to be going up. You're going to be going up if you walk in that direction. Okay, we will pick up with this. We'll pick up with this. There's one other thing we need to talk about with directional derivatives. And that's this, and we'll answer that on Monday. Which direction would you get the most increase? Does that seem important? If it's profit, which direction would you go to get the most increase? And we'll talk about that on Monday. Have a safe weekend. Have a safe weekend. Stay COVID free. Stay COVID free. Thank you. Thanks, Stuart.
Yeah, we get
Oh, thanks. See you, Nick.
There goes Robert. Good one. Could you
Yes.
explain real quick what the gradient like represents again?
So it's in the domain. It's two-dimensional. So what we're going to show is that because the directional derivative is the gradient of f dot u, and you might remember a dot b is equal to the norm of a times the norm of b times the cosine of theta.
Yeah.
That this could be the same thing as the norm of the gradient times the norm of u times the cosine of the angle between u and the gradient. So you're down here in the domain, you've got your space sheet above you, you're at some point here, and you've got some unit walking along there,
Yeah.
and you're saying, okay, well, the derivative in this direction is the norm of this times the norm of this, but this is just a unit vector, so that goes away. The largest cosine, theta is the angle between the gradient, the angle between the gradient and the unit vector. But cosine is stuck cleanly between, the largest it can be is 1, and the smallest it can be is -1. What angle, theta, would give the biggest directional derivative?
0 or pi.
0 or pi? Well, yes. If it was 0, then it would give the biggest positive direction. if it's pi, it would give the biggest negative direction. And so what we see is that the gradient, out of all the directions you could go in, the gradient points in the direction where you get the most increase.
Okay, got it.
And if you go just opposite, you go in the pi direction, you're gonna get the greatest decrease. And so what you'll see is a lot of three-dimensional stuff, they'll do gradient graphs. And so they'll look at the domain, they'll chop it up evenly, and then they'll plot the gradient of the surface at all this, and it's a gradient graph, and then somebody can follow and say, well, what path, if I start here, would give me the maximum? And you just kind of follow these curves around, and it gives you a rough way of trying to determine. You'll see it a lot in weather modeling, these. So we're just beginning, but I like to think of it as, if I'm standing on the side of the curve, if I'm standing on the hill, the gradient, which has the greatest gradient? You know, if I was gonna think about the gradient of this thing, the steepest tangent. Oh, all I need to do is sit on the bottom and send my robot, you know, if I'm trying to do it on Mars, I'm gonna look at my domain here and be like, okay, I'm gonna go there, and it's gonna go like this. If I know the surface, I can just send my robot along using that gradient. You know, I go here, and then I'll readjust my gradient vector, recalculate it, I'll go this direction. Take another step, recalculate it, and I'm gonna do my best to try to follow the maximum path.
So if you found it in the domain like that, where it was like the max with the cosine angle, would it reflect in the range and like the space sheet, the steepest, or where the space curve is changing the most?
That's
like
exactly.
where the curvature is the most?
It was not quite curvature, but it would be the steepest descent.
Okay, got
It
it.
would be like if you're taking the steepest descent up the mountain,
Okay.
that would point that way, which you probably don't want to do. But it may be the fastest, but it may not be the safest.
Yeah.
And so they'll often use the gradient as some kind of measurement. You know, keep your gradient between here and here. You know, you don't want to kill them.
Yeah, exactly. Right.
But it's so cool. I mean, all this stuff is just so. It has so many applications, and it's so cool. And then the class just ends. You know. And then
Yeah, I know. See, I'm a finance major, so I don't get to think about it like physical.
No, right. You get to think about it in you know, profit.
Exactly.
You know, and for you, that's even more like, okay, my job depends on this. Are you
Yeah.
quantitative finance?
I'm not keeping, no. I'm just like kind of picked up a math minor for fun, honestly. But now I'm like kind of wishing I did a math major, but I don't have the space to do a double major. So.
I mean, it's really, yeah, I have kids who are at quantitative finance that have been out for 20, are you keeping?
That's what I was gonna ask.
Yeah, they're like, you know, and when they actually get to the real world, and I'm like, well, like, how much do you actually use? And I'm like, not much.
Yeah.
And they go, but the biggest thing is, like, there is no such thing as a 95 being good, you know? It's either, you're either a 99 or an F, you know? There's not anything in between, so it's always the stress. But they're like, you know, Dr. Warren, you know, what's your salary? And and then they'll be like, I'm making double your salary. And I'm like, that's awesome. And I'm like, you're working twice the hours.
Yeah, you're working 100 hours.
You're working twice the hours. And I'm like, no, you're right, I'm working twice.
Yeah, exactly. I didn't realize that until recently. I was like, man, I don't want to do finance. I want to work that much a week. I mean, that salary's not even worth it.
Oh,
So I was like, I wanted to switch to a math major, but at this point, I might as well finish up. So
I thought about going into business with my applied math degree, but
yeah.
I love teaching too much,
Mhm.
you know, so that's my passion, and so,
Yeah.
and then seeing my students succeed, that's my biggest passion, you know.
Mhm.
15 years from now, when I see where you guys are at, because I've been blessed, my students will still let me know and give me little windows into their lives, and so
Yeah.
it's fun just seeing you guys and where you're at, and how you're vice presidents at one point in time, and yeah, it's.
Well, thank you, Dr. Warren.
All right.